Okay, so I'm just trying to resume what we discussed last time before, just right before interrupting. So we were talking about thermal and black body radiation. In particular, we consider first of all, I have to just a brief comment. I'm sure that any of you already are somehow already familiar with black body radiation. In many courses, many previous courses of your studies, of your previous studies. In this context, in the context of radiative transfer, we will be we will be seeing some new aspects. In any case, put in a different context. So we will then of course you are free to comment at any time. So just let me skip quickly up to the point where we left last time. So we saw that in order to make sure that the second law of thermodynamics is not violated, necessarily the intensity or the brightness associated that is coming out of the surface of a black body with a temperature T just depends on temperature and it's a universal function, which is the Planck function. And in particular, we found out that for a body in thermal equilibrium, so with a given temperature T, the source function itself is the Planck function. And this can be easily seen just by looking at which I put here, the radiative transfer equation in the case of the radiation field that you would expect just close to the black body. So the intensity has to be constant. Otherwise, you would have had a net exchange of heat, which cannot be the case in this case. So necessarily, the derivative of the intensity with respect to as soon as you move along some path, with respect in this case to the optical depth, has to be zero, which means from the radiative transfer equation here that the intensity has to be equal to the source function. So the very last thing that we were commenting last time, was the so-called Kirchhoff's law, which makes a very important statement. So it establishes a link between the emission coefficient, J nu, and the absorption coefficient of the same matter. And in particular, their ratio is just the source function, so the Planck function. So the two abilities, the two properties, the two kinds of properties of both emitting and absorbing radiation for a body, for some matter in thermal equilibrium, so characterized by a given temperature T, is a universal function, which is the Planck function, and so called the Kirchhoff's law, after the German scientist who discovered in the 19th century, something like that. So it's worth considering the radiative transfer equation in the presence of thermal radiation. So when the source function is due to matter which is in thermal equilibrium. So just if you want, just because of the Kirchhoff's law, you've got matter in thermal equilibrium at given temperature T, so you already know, automatically, you know the source function associated with this matter, okay, S, which we call B nu, as a function of temperature, the Planck function, which we will see repeatedly in a few minutes. What's the difference between thermal and black body radiation? That's one of the most important points here. When you've got just thermal radiation, it means that you know the source function. If the matter is in thermal equilibrium, the source function is known and is exactly the Planck function, which just depends on both frequency, of course, and temperature. Nothing can be said in addition to that. Just thermal radiation. Black body radiation is a stronger requirement because not only is the source function, but it is the intensity itself, which is the Planck function. So it is a stronger requirement. If you are just in the presence of matter in thermal equilibrium and nothing is said about the radiation field, it could be the case that the source function is necessarily the Planck function, but nothing is known a priori about the intensity. So in that case, you can just speak of thermal radiation, not necessarily of black body radiation. This is worth thinking about. So my advice is just think about it carefully. As I said last time, even some senior researchers in the field sometimes make confusion between the two. They speak in terms of thermal radiation and they have in mind black body radiation. They're not the same. When are they equal? Well, think about, again, radiative transfer. You know that provided that the size of the source is optically thick enough, so when the optical depth is much larger than 1, so the medium, the source is optically thick, you know that the intensity approaches asymptotically the source function. So it means that when you have a thermal source, matter in thermal equilibrium, and the source is optically thick, automatically intensity is very close to, is essentially the source function, which in this case, in the case of thermal equilibrium source, is indeed the black body function. So indeed, thermal radiation becomes black body radiation for an optically thick source in thermal equilibrium. Okay, so if you have a source which is in thermal equilibrium and nothing is said about, for example, its optical thickness, you cannot automatically infer that the intensity associated with the source is the black body. You do not know. It could be different. But if the source is in thermal equilibrium and in addition, the optical depth of the source is much larger than 1, which means the source is optically thick or opaque. In that case, thermal source plus optically thick, the result is that the intensity itself is also the Planck function. Okay? And this is something we already knew from the considerations that we made last time, okay, about in which cases the intensity approaches the source function. So in this case, it's particularly interesting, particularly relevant, given that it's a special case in which we can say a lot about the source function. So I've been talking about the source, the Planck function for a while, so it's worth reminding ourselves what it looks like, and in particular, well, I'm sure you're already familiar with the frequency dependence. So nu cube over the exponential that you see, which, well, there could be a lot of comments about this formula. For example, about the distribution followed by bosons. Photons are bosons, so you could recognize the Bose-Einstein distribution, but I don't want to focus on that. Instead, pay attention that B, from a dimensional point of view, is intensity. So you might make sure that indeed, according to the constants that you see, the Planck constant, the speed of light, and frequency, this is indeed from a dimensional point of view, this is intensity. I think this formula is so important for a physicist. It's worth learning by heart. So I would invite you to make sure. And as particular, I here wrote K also in addition to H, also so the Planck constant. I also wrote the Boltzmann constant K. These are a couple of constants, in particular H. I think that a physicist should always at any time in their lifetime know the value of the gravitational constant, capital G, speed of light in vacuum, C, and H. So if you don't know the value of H, there's no point. And I would say also K, also is very useful, K. So so I just put here the values, their values in the CGS system, okay? From that, you can derive the bolometric intensity. So if you integrate the specific intensity of the Planck function, so integrate over frequency, along frequency between, of course, 0 and plus infinity. And this is something, this is an integral which looks this way. And I'm not going to spend any time. This is just calculus stuff. So I'm not going to comment why the result of this integral is just pi to the 4th power over 15. Just I let you have fun and see how where it comes from. The important point is that okay, you can rearrange all these terms. You see all constant except for in addition to pi's. There are just Boltzmann constant, the speed of light, and Planck constant. And here I wanted to highlight the dependence on temperature. So temperature to the 4th power, which again is something that I'm sure you already know, and you probably learned it from different courses. This is useful because you can also express all this result in terms of sigma over pi, where sigma is the Stefan Boltzmann constant. If you remember, so first property to note is the temperature dependence. So the bolometric intensity scales with T to the 4th power. You have to know that. There's no way a physicist cannot remember this. First point to see. The second point, the constant is just sigma over pi. If you remember the Stefan's law gives you the flux of a black body, which is indeed sigma temperature to the 4th. But the flux, I remind you, is energy per unit area per unit time. This is B. This guy is B. So it's the same. Energy per unit is B integrated over frequency. Sorry. So it is energy per unit area per unit time per unit solid angle. So with respect, if you compare it with the flux, with energy flux, and I don't specify flux means energy flux. There is just a difference in the per unit solid angle. So here, with respect to, if I had written sigma temperature to the 4th, it would have been a flux. So energy per unit time per unit area. But here I integrate it over frequency B. B is in intensity. So what I should find in the end is flux over per unit solid angle. That over pi just is reminiscent of that. And not only that, but if you remember one of the results that we obtained 1 week ago, when we derived the relation between the flux and intensity for a uniformly bright sphere, there was a factor of pi in between. So we derived that the flux was pi times intensity. That's exactly what we find here. Flux over pi is intensity. So we match the same. We find a connection with what we've already derived a couple of classes ago. So all this makes sense. It's useful. It's not mandatory, I would say, but it's useful in your lifetime as a physicist, particularly where you're dealing with black bodies and thermal radiation and black body radiation. It's useful to remember the sigma value. It's easy to remember. Well, probably it's easy, even easier in the international system. In the international system is 5.67 10 to minus 8. In this case, in the CGS is 5.67 10 to minus 5. Up to you. You are not required to, but if you know it, it can be very useful in many calculations. What is this? Well, on the left is so the Planck function, and I wrote it as I already wrote in the previous slides as B nu. So this is a specific intensity, where specific means per unit frequency. If you are fonder of, if you prefer as a function of wavelength rather than frequency, when you can express the same quantity, so the Planck function has a specific intensity, but in terms of, instead of per unit frequency, per unit wavelength. So what would be natural to call B lambda of t. What's the relation between? Well, you have to make sure that B nu, d nu equals B lambda, d lambda, because that's the same amount of energy that has to be equal. So when passing from one to the other, you have to derive the relation between lambda and nu. You know that they are just reciprocal. Lambda is c over nu. So that's why on one side you have lambda to the 5th power, on the other side you have just a nu cube. There's a factor of, there's a power of, extra power of 2, which comes from. Okay, so it has a slightly different it appears to be slightly different, but again, the Planck function, no matter the way, so whether it is expressed as a frequency specific in the frequency sense or in the wavelength sense, it has a peak. So let's focus on the left. If you think in terms of frequency, you find that the frequency at which the Planck function peaks, which we call nu peak, is roughly 2.82 kT. So it scales with kT. So the hotter the matter, and correspondingly larger the peak frequency. If you play the same game with the Planck function in terms of lambda, again, you find that what is usually known as the Wien law. The Wien law states that the peak, so the lambda, the wavelength at which the Planck function peaks, which we call lambda peak, times temperature, is close to 3 millimeter per Kelvin, more exactly 2.898. This is called Wien function. This is also very useful to remember, because whenever you know the temperature of a body, you can immediately work out the wavelength at which the Planck function peaks, and the other way around. If you expect that the two corresponding quantities, on one side, the peak frequency, on the other side, the peak wavelength, are corresponding to one another, so in particular their product is just C, you will be disappointed, as you may check for yourself. The question is there a contradiction? I'm not gonna give you the answer. I would like first that you think about it, not just now. I can tell you the answer possibly tomorrow. You have to think about it. Is this contradictory? It may be subtle or not, depending on the way you look at it. It might be not so, it might be slightly, but this forces to think carefully about the meaning of the Planck function in one way and the other way. So let's review some very important properties of the Planck function. If you take two bodies, two black bodies in particular, having different temperatures, and you compare the two laws, you will see that the hotter will have the intensity greater than the cooler one, and this holds at any frequency. So the full Planck spectrum for a hotter body is higher than at any frequency than the cooler one. There are also two regimes which are particularly useful to explore. I'm sort of essentially, for some aspects, I'm supposed to be repeating just what you're already familiar with, but I think it's worth it. So the so-called Rayleigh-Jeans regime, which is the regime in which you are interested in a frequency range where the frequency is very small. How much? Well, h nu, so the typical energy of a photon in the frequency that you are interested in, is much smaller than kT, where kT, if you remember, is of the order of the kinetic energy, of the order, not exactly, of the average kinetic energy of the matter, okay, of the individual atom of the matter. So in this case, if you just Taylor expand the denominator, you see that the denominator goes like, is proportional to nu, so in the end you're left with nu squared. So the nu square scaling is a kind of signature of the Rayleigh-Jeans regime, okay? And in particular, I becomes, well, this is easy to see because you see here the denominator just is Taylor expanded at first order is just h nu over kt, so h and h cancel out. So and you are left with 2 kt over c squared nu square. Easy. So just to denote the regime, I just put here in the superscript Rj to mean, of course, Rayleigh-Jeans. This is somehow the so-called classical limit. Classical in the sense of where quantum mechanics doesn't come into play, doesn't show up, doesn't show. Why? Well, you see that, for example, the Planck constant doesn't show up. Again, here I could say a lot of things about ultraviolet catastrophe, but I don't want to, something that you already know. The opposite regime is, of course, when the frequency, the energy of the photons that you are considering is much larger than the kinetic energy of the single atoms of the matter, which is responsible for this radiation, so-called Wien regime. So when h nu is much larger than kT. So in this case, okay, you see that the denominator is just dominated by the exponential term. So you can approximate, you just, in the denominator, you can neglect -1, which is negligible with respect to this term, which becomes much larger than 1. And so in the end, you've got the same guy here. Okay, I think I skipped here. I definitely skipped a Planck constant here, which should be here. Okay, just look at that, and of course you immediately see there the Planck constant is missing here. Anyway, another quantity which is useful to consider when you are dealing with intensity, which describes our radiation field that we have in mind, is the so-called energy density. And we will see here in particular the case of energy density for a black body, given that we are examining, we are considering the black body radiation. But in general, energy density can be associated with any brightness. And what is that? Well, just the name speaks by itself. So it's the energy per unit volume associated with a given radiation field. And there's a particular relation. In this case, energy density is the integral, so it's a bolometric quantity, and bolometric integral of what? Of the specific energy density, which I called here U nu. So U nu is the energy per unit volume per unit frequency interval, okay? So if you want to move from the specific energy density to the bolometric energy density, which is exactly what I'm calculating here, just again, once more, when moving from specific to bolometric, just integrate along frequency. For an isotropic field, I'll prove in the next slide that the relation between the specific energy density and the brightness is just this relation that I put here among brackets. So there's a factor of 4 pi over c between the two. I'm going to prove it in a moment. So let's take it for granted now, okay? I'll prove it right after this one. So, okay, so it means that instead of the specific energy density, I can put 4 pi over c and b nu, because we are talking, in this specific case, I'm talking about black body radiation. And we know that that guy is sigma over pi. So sigma over pi times 4 pi over c, you are left with 4 sigma over c, which in the literature is usually denoted with A. Here this constant, which I call A, is not my own choice. It's a standard notation. So again, this can be useful also to learn, even not, it's not necessarily useful to learn by heart, but just have your, if you have a page, a kind of notes, special note in which you write down all the most important quantities that you want to remember to have, that can be used many times. This is one of them. Because A, temperature to the fourth, gives you the energy density, so total energy density already integrated along frequency. So this is indeed energy per unit volume, and that. So as a consequence, also the units of measure of A is energy density. So erg per cubic centimeter, and given that times t to the fourth power has to be energy density. So this is Kelvin to the minus 4. So you see, again, energy density, given the energy density, and in particular, the specific energy density is proportional, scales linearly with intensity, with the associated intensity. In the case of black body, the specific intensity is the Planck function. And when you integrate along frequency, there is a fourth power dependence on temperature. So the same kind of dependence is inherited by the energy density of black body. So these are kinds of dependencies which are very important. You should always know that. Then my advice is you can forget about the specific values and constant, but not the very important one that I just mentioned in the previous slides. But I mean, as a matter of fact, if you're not used to use frequently kinds of constant like A, well, there's no problem with not remembering it. But you should always remember the dependence with temperature. So in this case, this is very important. So I was foretelling you that here now we are going to prove the relation between energy density and brightness. So let's see where this 4 pi over c comes from. So let's consider we are, for example, within a star, we are within, so below the surface of a star. So there is energy flowing in any direction. We assume an isotropic field, so there is no preferred direction. All are inside and all directions are characterized by the same flow of energy. So let's gain some names. So with U nu, that's what I called before the specific energy density, which means, okay, energy per unit volume per unit frequency. So let's assume that we consider a given volume that I'll describe more specifically in a moment. Out of all the photons that are moving to all directions, we want to select the photons that are moving within a specific solid angle, d omega. So because of the isotropy assumption that we made, it means that we have to select a fraction. The fraction is just d omega over 4 pi. So this is the fraction calculated with respect to the total solid angle, the fraction of photons that will be moving along within a given solid angle. So now I want, let's consider a surface element dA. Let's consider a time interval dt. We already mentioned d omega, so I wonder what's the amount of energy which crosses the surface element dA within a time interval dt, having frequency between nu and nu plus d nu, and moving within the solid angle d omega. Let's calculate this amount of energy that I just said. Well, it means that you have to calculate the volume that will cross the surface element in that given time dt. So let's have a look at that, at the figure. You have, well, the photons are traveling at the speed of light, c. So the volume has the base, which is of course the area of the surface element itself. So dA times the height, if you want, of this volume, which is c dt, which is the path traveled by photons in a time interval dt. So this is the volume that will cross the surface element within the time interval dt. I have the volume, now just multiply by the energy density, which is U nu, but mind the energy density times what? Well, first of all, times the frequency interval, d nu, because we want to select just photons having frequency between nu and nu plus d nu, so you have to multiply if this is specific. But not only that, you also have to multiply by the fraction I was mentioning before, d omega over 4 pi, because you are selecting all the photons, just the photon moving within that solid angle. So this is energy, because you see, energy density, so per unit volume, and this is the volume, I multiplied by the volume. Specific, so per unit frequency, I multiplied by the frequency interval, and I just selected the solid angle. But this is also, if you remember, the definition of I is energy per unit area, per unit time, per unit frequency interval, per solid angle. So this is just I times d omega, times dt, times dA, times d nu, just like that. And so, but just, so you see all the infinitesimal quantities just vanish. So you're left with a relation for an isotropic field. I stress that. Again, when you see, again, 4 pi, it means that there is something which is averaged out over the solid angle, or something which is which relates to an isotropic field. Whenever you say 4 pi, there is always this, an argument like this. So you see that in this case, the relation is very general. Provided that the field is isotropic, In the previous slide, I used this in the specific case of a black body. So when I is B, but it's general, very general. As soon as I is isotropic, you immediately know the energy density, the specific energy density. Specific, yes. So when you integrate your along frequency, then you have the corresponding bolometric quantities. Okay, let's keep on reviewing definition and properties about black body radiation. If you have in mind of the black body in the Rayleigh Jeans regime, so what we call this I nu Rj, you can easily invert the temperature, so you can express temperature as a function of the remaining quantities. If you do that, you end up with the definition of a new quantity, which is called brightness temperature, which is denoted with TB. And what is that? Well, let's assume you measure I, so the intensity of the field. Well, if this is indeed the intensity of a black body, well, it's straightforward to infer that what we call here brightness temperature, TB, is indeed the temperature of the black body. It's just because we inverted the Rayleigh Jeans formula. So it's, I mean, it's like a hot water discovery. There's nothing interesting in that. The interesting aspects comes when the intensity that you are considering is not necessarily no more related to a black body. So if you just have a radiation field and you measure a given intensity, well, you can immediately, automatically associate with the temperature. You can define the concept of brightness temperature, and you call it TB, just using this formula. And if you think about it, just by definition, by looking at that formula, you immediately realize that this definition defines a property of radiation. You have some radiation field, you measure I, you can define this quantity, which is indeed the temperature. If the radiation has nothing to do with the black body, well, it means that the brightness temperature has nothing to do with the temperature of a real black body. What you can think of is that you measure a given intensity, well, the brightness temperature is the temperature that a black body should have to give you the same intensity at that frequency. That's useful. So I state it again. So whenever you have an intensity field or radiation, you measure brightness and brightness at one point at a given frequency, you can define the brightness temperature. You see, brightness temperature because it's the temperature defined as a function of brightness, starting from a given value of brightness. So the brightness temperature is the temperature a black body should have in the Rayleigh Jeans regime in order to have the same intensity at that frequency as the one that you measure, that you have, that you start with. Another property, again, this is also very useful. We will exploit it also in one simple exercise. A black body is the so-called most efficient radiator of thermal plasmas and incoherent radiation. What does this mean? Well, let's see the requirement. You have a given source. The source is in thermal equilibrium, has a given size, and the emission is incoherent. What does this mean? Well, it means that all the atoms that are responsible, all the atoms that belong to the source and which are collectively responsible for the emission, they do not emit coherently. Just like that. Every single atom works independently of the others, okay? That's just what incoherent means. So provided that you have a source which is in thermal equilibrium, which emits incoherently, a given source with a given temperature cannot have an intensity larger than the black body with the same size, with the same temperature. So imagine you have a source. Imagine you fix the temperature. Imagine you fix the size of the source. Well, the intensity coming out of the source, provided that it's emitted incoherently, cannot overcome the intensity cannot emit more energy of a black body having the same temperature, the same size. Okay, so the most efficient radiator, the luminosity, so energy per unit time emitted by a source with a given size, with a given temperature, cannot be larger than the luminosity of a black body having the same temperature, the same size. That's so in other words, that explains the sentence that a black body is the most efficient radiator. It's important also to remember the conditions. So provided that radiation mechanisms is incoherent, because if you relax this assumption, you can violate this. We will see an example in the end when we will be talking about Einstein coefficient. Yes, we will exploit this property in many different contexts. So we will have occasion to see applied and to appreciate the powerfulness, the power of this property. And of course, provided that you know that a given body, so for example the sun, can be reasonably approximated to a black body, well, you can estimate, for example, the luminosity, provided that you know the temperature and the size. Or you can invert. If you know the luminosity and you know the size, you can derive the temperature. Why? Because the flux is supposed to be described by the Stefan's law, sigma T, temperature to the fourth power. So an easy example is just the luminosity of the sun can be approximately calculated as the surface of the sun, 4 pi r squared, times the flux of a black body. So sigma temperature to the fourth is energy per unit area per unit time. You multiply by the area of the surface of the sun, you've got energy per unit time emitted by the sun, which is the luminosity. In astrophysics, I remind you, luminosity is just energy per unit time emitted by the power emitted by an astrophysical source. So in this case, we know the luminosity of the sun. A way of measuring, for example, is to exploit what I called in the previous classes a so-called solar constant. The solar constant is the flux. Energy per unit area per unit time emitted by the sun, which we derive 1.3 kilowatts. You know the distance, so you can measure the luminosity, which is 3.8. It's also useful to remember. I'm not asking you to remember necessarily, but if you remember the luminosity of the sun. So luminosity, so this is already bolometric, okay? This is already integrated. So you can use the Stefan's law and just inverting this relation, you can derive the temperature, which is nearly 6,000 degrees, as you already know, probably. We will see how close the spectrum of the sun resembles that of a black body. But if you think already, you can guess that the optical depth of the sun is much larger than 1. There's no way a photon created in just well within the sun can just make it out without scatterings. We will calculate how many scatterings a photon has to undergo when a photon which is created close to the center, where nuclear reactions actually take place. And in addition to that, we know that those photons are created as gamma ray photons. So they travel out to the surface we will calculate how long it takes. Probably you also calculate, probably you carried out this exercise also in other courses, probably, presumably, not necessarily. We will see here in the context of radiative transfer. So all this just to say that you can easily imagine that the sun is overall a size which is really optically opaque. The optical depth of the sun is huge. Even just simple because if you look at the sun with the dew filters, you just see the surface, or better, I should say, the photosphere. You don't see inside. So this means that the source is opaque. So the optical depth of the source of the sun is much larger than 1. The sun is more or less in thermal equilibrium, so you've got a source which is thermal equilibrium, optically thick, like body. So the intensity is the case I was mentioning before. And you've got a thermal source whose optical depth is much larger than 1. It means that not only is the source Planck function, but also the intensity is the Planck function. So what you measure. And indeed, so that explains, at least from a qualitative point of view, why the sun spectrum is reasonably approximated by a black body one, because it's an optically thick thermal source, just like that. Now you should see, oh, now I see why radiative transfer is useful. It provides me with a new way of looking at it. If you are feeling like that, well, you are on the right path to a deep understanding of radiative transfer. This is a plot that we will encounter again in some weeks. But here, I just wanted to show you because it visually shows the point I was making about the black body as the most efficient radiator for a given source with a fixed temperature and fixed size. All these curves, well, the thick one is just the black body. So imagine you have a source with a given temperature, given size, and imagine that you can fill in more and more gas. The result of the intensity that you measure is that when there is not much gas, and at the beginning you measure this. Oh, by the way, this is intensity in the y-axis, and in the x-axis is frequency. Okay, so this is the plot of specific intensity. Okay, this is a log-log plot. So you measure the intensity as a function of frequency. So when you have not so much gas, so when the density of the source is relatively small, you see you have here at sufficiently low frequency, the intensity is very close to the black body one. And here, this region is where you are at sufficiently low frequencies. If you remember the two regime, it means Rayleigh-Jeans regime. And at some point, at some given frequency, there is a significant change in the behavior. Above some frequency, in this case, this frequency here, then the black body radiation starts being significantly higher. And then here, and the effect of increasing density by keeping the same temperature and of course the same size of the source is just that gradually you see that the intensity as a function of frequency gradually resembles more and more approaches the one of the black body. What's the effect of increasing the density of the gas? Well, if you increase the density along the given path crossing the source, it means that n number density is increasing. As n increasing means that the absorption coefficient increases. So the optical depth itself increases. But we know that if you keep putting gas, adding gas, you increase density. By increasing density, you increase the optical depth. So you gradually move from a tiny frequency from an optically thin regime to an optically thick. But we know what happens in terms of brightness when moving from an optically thin to optically thick regime. That intensity gradually approaches the source function. The source function is a black body. So that's why you see visually, you visually appreciate the effect of a source with a given temperature, a given size, which becomes gradually optically thicker up to the point when it is really optically thick at any frequency. When it is optically thick at any frequency, the resulting spectrum, the resulting brightness will match the black body one. So you see that optically thin is also something which depends on frequency. And we will see that again. But here in this regime, you see that the brightness essentially already almost approached the black body intensity. So it means that in this frequency range, the body is already optically thick. While the same body at larger frequency here is optically thin. So it means that when you are, this is something we already knew, because when we kept speaking about optical depth, absorption, we always have in mind specific, so something which depends on frequency. But here we see that. We see that the same source, so the same guy here, can be optically thick at this frequency range, and in this frequency range is optically thin. But if you keep putting gas, adding gas and increasing density, you pass from here to here. So you see that, for example, in this intermediate frequency range here, when you were in this case, the source was optically thin, and now here is optically thick. So it means that if you keep increasing, you reach the point where at any frequency, the source is optically thick. So when it is optically thick at any frequency, that's the case in which the resulting intensity field exactly matches, is almost identical to the source function, which is the black body, Planck function. Which, in this case, you see that why the most efficient radiator? Because all the intermediate cases, they are lower. So at any frequency, the intensity of these cases is always smaller equal. That's why you clearly see that the integral, if you calculate the integral of these functions, which is exactly the bolometric intensity, so energy per unit area, per unit time, per unit solid angle, and that's it. You immediately see why the black body is the most efficient radiator, because it has the largest area. Area in the sense of integral, I mean, in this figure. Okay, we will get back to it, and we will understand more exactly the thing I was commenting about, the dependence of optical depth on frequency. That at sufficiently low frequency, the body becomes optically thick, while at larger frequency becomes optically thin. Why? Because it's the absorption has a dependence on frequency, which is typically the lower the frequency, the larger the absorption coefficient. So when you have a greater absorption coefficient, it means that the optical depth is correspondingly larger. Okay, here now we will see quite quickly, I would say. I put several of them because they provide us with several ways of looking at it. So the black body spectrum, either as a function of frequency, so specific in the sense per unit frequency, or specific in the sense of per unit wavelength, just to let you become a bit familiar with typical values. So for example, you see that in the so-called visible portion of the electromagnetic spectrum which encompasses frequencies between infrared, near infrared, and close to the bluest filter, blue, close to ultraviolet. So in this case, you see, for example, these are all black bodies shown at different temperatures. So again, you see that if you work out, again, this is a log-log plot, okay? So do not be confused by that. So for example, you would expect that the integral of all these functions scale with temperature to the 4th power, okay? And you also see, for example, the property I was telling you, that if you take two black bodies with different temperatures, they never cross. So the hotter one is always larger at any frequency than the blue one. And in particular, here you see that you have a black body with a temperature of a few thousand degrees. The peak frequency is close to the visible spectrum. Here you also have the scale, the corresponding scale. Of course, their frequency and wavelength are reciprocal to one another. So, of course, the increasing one is decreasing one, and the other way around. Again, this is another plot, very similar. Here, the y-axis is indeed, because sometimes you have flux, and they express the y-axis is flux density. This is just brightness. So this is just, you see, watts per square meter per hertz per steradian. So this is just our friend intensity in log scale, of course. And this is also useful because it gives you the typical, with names, the typical frequency range. So between radio goes up to 10 to 11, kind of 10 to 12 almost. And then you have the infrared, the optical, which I prefer. Yes, optical, yes, is okay. Then the ultraviolet, then the X-rays, and the gamma rays. So you also see, for example, the corresponding energy. So, for example, that's why compact objects, like we have many in our own galaxy, with surface temperature of several million degrees. Million degrees, it means that you are here, around here in this region. So it means that the peak, most of the energy will be emitted in the X-rays. So this plot is useful to have an immediate way to see where, well, you can use the Wien law on the corresponding law in the frequency, but this is a way of graphically putting the same. Again, this is again more descriptive if you want. It gives you also some reference. I apologize for the German, but I think it should be straightforward. I found this just in. So, well, the name of the colors is straightforward because just look at the color. So there's nothing difficult in here. What I can say, well, it's everything obvious. Wellenlänge is just wavelength, obviously. Fernsehen is television. So you see also the frequencies typically used by the broadcast with the televisions. Mikrowellen is microwaves. Röntgen, though this is the only thing that you probably might not know. I don't know if you know that. X-rays in German is Röntgenstrahlung. Röntgen, after the name of the scientist, who was a German guy, at the end of the 19th century discovered. Now, there's also a funny story about that, because I know he was a very humble guy. He didn't like the idea that, he didn't want that radiation to carry his own name. But apparently the Germans just did it anyway. So if you travel to Germany, you want to mean I had to have X-rays for my, I don't know, for your health, and then you have to say Röntgenstrahlung. So this is kind of funny thing. Again, this is exploits more in detail the different wavelengths, in this case, of the visible part of the spectrum. Okay, das würde Menschen sichtbare Spektrum des Lichts means the spectrum of light which is visible for a person. Yes. Again, so you see, in this case, you have infrared and ultraviolet. So you also see the typical wavelength. So 550 nanometer is just the green, and the red is just towards 800 nanometer, and the blue is just around 4, more than 4. And again, here you see a lot of things that can be useful to see. You have here both the wavelength and I don't know, you have the frequencies. No, it doesn't look like. Anyway, the frequency is increasing. The frequency is increasing from left to right, and obviously the other way around concerning frequency. So Wechselströme means alternate current. Mittelwelle, middle waves, long waves, as I said, television, Ultrakurzwelle. Okay, this is just to let you, to provide you with several references, which are useful also for your own. Okay, so another way of putting it, again, this is just intensity as a function of frequency, again, for a black body. So again, you see joule per second, per square meter, per hertz, per steradian. And here I put the reminder of the law, which gives you the peak frequency, so 2.82 kT. And here the temperatures, I shown here several black bodies with everyone with its own temperature. The properties of black body radiation is that when you measure some given intensity at a given frequency from a source which you know, for some reasons, you know that it is a black body, from just one measure of intensity, you can immediately estimate the temperature. How do you do that? Well, you simply exploit the property that you can never have two different black body spectra which cross each other. They never cross, you see. None of them are crossing. So it means that if you know, for some reason, you make a measurement, let's suppose you make a measurement at this frequency, and you know, and so you choose the frequency. Choosing the frequency means you choose the point along the x-axis. You measure you measure the resulting intensity, so you find the value along the y-axis. You know, for some independent source of information, that the source is a black body, so there will be only one black body whose spectrum will pass from here. Okay, and so you immediately infer, you measure the temperature. You explore, because otherwise, if you had two different black bodies which would cross, you could not. Let's suppose you measure that point. How do you know where it is one or the other guy? No, you exploit the property that they never cross. So whenever you make one single measurement, you measure one specific intensity on one given frequency, and of course you have to know that that's a black body, because otherwise you cannot exploit the properties of the black body. You can immediately estimate the temperature. This is the Planck spectrum, now as a function of wavelength. So here you recognize the same law I was showing before. Again, in this case, here the colors highlight the visible portion of the spectrum, so which can be seen by human eyes, of course, corresponding in this case for a body of 6,000 Kelvin, which is essentially the case of the sun. This is the same plot showing you how the lambda, the lambda peak, so the peak of the black body spectrum as a function of frequency, changes as a function of temperature. So this is a way of graphically show the Wien law, if you want. Oh, this is a point interesting I wanted to make. You might have heard, as I did at the time, that, okay, you see, human eyes are made in such a way that they've become especially sensitive to sunlight because of evolution, because of Darwin's evolution, if you want. So you see very well in the visible portion, because that's the frequency interval in which the sun emits most of its energy. So for some kind of evolutionary convenience, our vision became especially effective in just became especially sensitive to the radiation emitted in that frequency range, because that corresponds to the peak of the Planck function for the sun. So it's beautiful to think of this, no, isn't it? Because you think of this as the result of a million-year-long evolution. That's wrong. It's not true. It's a story which is repeated many times. So that's why I said a common misconception. And a way of putting it, also not only a human eye here, as I wrote, but also the fact that most plants are sensitive to green, because no way, it's not true. Nothing like that. Why? Well, you can appreciate that if again you work out, you show the spectrum specific in the sense of per unit frequency on the right panel here, and you do the same exercise as a function of wavelength. So the red lines that you see, it's measured, it's indeed the spectrum measures of the sun, both cases. So you make a fit, you model with a Planck function. Of course, in this case, this is frequency, so you have to use Planck function expressed as per unit frequency, and you find out that the function, the values which are best approximating what you measure, corresponds to a new maximum of 3.4 10 to 14 Hertz. If you work out the corresponding lambda, C over nu BB max is around 882 nanometer, which is close to infrared. It's between red and infrared, so very red filter. If you do the very same exercise, so you measure, so the red points here, the red line is what you measure as a function of wavelength. You take the Planck spectrum as a function of wavelength, you work out which is the one which best matches the measured flux density. You see that the function has a lambda max of 500, essentially 501 nanometer, which is green. Green, blue, no, more green than. So it's not true. Depends on the way you. To figure out that there is no indeed contradiction between the two, this requires you to think of what I mentioned at the beginning of this class when I asked you, is there any contradiction that lambda peak times nu peak is not C? If you figure out that reason, you can really understand why this is. So it's not true, because the story that humans and plants and trees and whatever you think of just evolved in such a way to maximize the energy input from the sun. It's not true. And there's a paper in particular So this immediately, the two panels shows that, well, it depends. If you say green, if you assume wavelength, but you say red, infrared, if you say frequency. So what's the answer? So it's not necessarily true. And indeed, human vision works in a completely independent way. To let you appreciate, I don't want to explain too much in detail because I would like you to think about the original question I put at the beginning. I would like you to try make your own attempt to figure out why there is no contradiction between the fact that lambda peak times mu peak is not c. So after that, we will comment on why, as a consequence, this story, which is also sounds nice. Okay, it's beautiful to say that we evolved, plants evolved in such a way to maximize the energetic output from the sun. No way. There's nothing like that. So this is a link to a paper which explains more in detail. But before commenting on that, and I wrote, if you can, this is an hyperlink. So if you click on the PDF, you will be redirected to the paper. If for some reason your credentials, your university credential don't allow you to get the paper, just let me know. I can share the PDF. That's no problem. But before fully commenting on that, I would like you to think of the point I was making. Okay, let's go through this simple exercise to test ourselves about how much we understood about black body. So, of course, this is an astrophysical example. So the Orion Nebula is a H2 region. So it's a region where hydrogen is fully ionized, essentially, containing hot ionized gas that emits thermal radiation. At a frequency of 400 megahertz, the Orion Nebula is found to have a flux density of 200 Jansky and comes from an area on the sky with a solid angle of 2 times 10 to minus 5 steradians. Use these data to infer a lower limit to the temperature of the gas in the nebula. But before just seeing the calculations, let's try to figure out why the question makes sense. Well, we have a region with hot gas, and the gas is emitting thermal radiation. Thermal radiation means that the gas is in thermal equilibrium, but not necessarily black body radiation. Why? Because we don't know the optical depth. Is a region which is that region optically thin, optically thick? And if it is, or if it is not, at which frequencies? Is it optically thick? At which frequencies is optically thin? So we don't know whether by assuming a Planck spectrum, Planck function, we can, if we can assume the Planck spectrum as the intensity, which is what we measure, we know the flux. Can we assume the temperature? Well, we could measure directly the temperature under the assumption of our Planck spectrum. You know the flux, so you can infer. But here, we don't know whether it is, whether we can do that, because essentially we don't know whether the source is optically thin or optically thick. But I remember that the black body is the most efficient radiator. So if it is optically thin, it means that the resulting I, in any case, has to be lower than what I would expect from a black body. Okay, so that's why lower limit, because in the extreme case of a source which is completely optically thick, that would be exactly the Planck function. So intensity that they measure would be exactly the one, the Planck function. If it is not, it has to be lower than. In this specific case, as I showed you, in that figure that I showed a couple of slides previously. When you move to sufficiently lower frequency, the body is optically thick because the absorption coefficient at sufficiently low frequency is large. So large means that for a given size, the optical depth is large. But in this case, this is a piece of information which I give you. At 400 megahertz, the body is optically thin, is not optically thick. So indeed, the Planck spectrum in this case is an upper limit. So, okay, let's work out the intensity. We have a flux density. I remember the flux density is energy per unit area, per unit time, per unit hertz. What we miss to have brightness is just per unit solid angle. But we know the solid angle subtended by the source, which is another datum of the problem. 2 × 10⁻⁵, so just divide. And you measure the intensity, which is 10 to minus 19 watts per square meter per hertz per steradian. Now, this I has necessarily to be smaller, lower, equal than the black body. Black body calculated at that very frequency, which we know is 400 megahertz. So this has to be, we require this to be lower equal than. Equal would be equal if at that frequency were exactly optically thick. We already know that this is not. This is a piece of information which is not required to solve the exercise. So we just replace, you take B, Planck spectrum, you replace all the values of the constant, 2h n cube over c square. Here I just put the result by replacing the Planck constant. The frequency is 4⁻⁸ hertz, okay? Cube over c square. Here I carried out in the international system, sometimes. And then over exponential, here I already replaced h nu, and K here is just Kelvin, okay? Kelvin, so 0.0192 Kelvin over temperature. So you do this. This is just simple mathematics, so I'm not going to spend too much time. So given that this is an lower limit, temperature has to be greater than. Just like that. So you see, let's have an overall look. It's interesting because if you know that the region in space is in thermal equilibrium, from a simple measure of intensity, you can immediately set a lower limit. You don't know about whether at that frequency the source is optically transparent or opaque. But this allows you, in any case, you to set a lower limit of temperature. This is very strong property. You see? And equal, you know that the equality case corresponds to when the source is optically thick at that frequency. Otherwise, it has to be greater than. Greater than why? Because a black body with a fixed temperature is the most effective radiator. So if you want to have that value of measured frequency, you have to have, if it's not optically thick, you have to have something which is hotter than a black body. Okay, this is the second exercise. By the way, I'm stopping in. Well, we began. Okay, so I will stop in 10 minutes, more or less. I'm assigning you a second exercise. Next time, we will see the solution of both. I will share also a presentation with all the details of the solution of the first exercise I already assigned you, and this one. They are useful, so I advise you. We will see just as a normal class, but I advise you to carry out on your own, because that way you can see. So that's why I didn't share the solutions yet. I'm going to share next time. So we will see together all the passages, all the different stuff. So let's see together the text of this exercise. An electric stove, where you cook your food, is turned off and the heating element turns back to black. But the stove warning light still indicates that the stove is hot. An infrared sensor is aimed at the burner, so it's pointing at the burner, and the radiation at a frequency 3.33 10 to 14 Hertz emanating from the burner is determined to have an intensity of 1.46 10 to minus 28 watts per Hertz per square meter per sterane. So you measure intensity. What is the temperature of the stove burner? And what is the total flux of electromagnetic radiation emitted by the stove burner? I think this exercise is very up to date today, is very current. Most of us, most of the people just living in this world in this year are going through, are exploiting this effect almost every day whenever they measure your temperature. Have you ever wondered, as a matter of fact, from a physicist's point of view, what actually this apparatus measured? It measured intensity. It measured intensity. So that's why it makes sure that the field of view of the measure is just that. That's why they come close to you. Because the solid angle has to fill in the field of view of the instrument. They measure intensity. By measuring intensity, they measure temperature. Just like that. In the very same way, this exercise is asking in the point 1. You know, of course, at a given frequency. In this case, the frequency is near infrared. They are infrared apparatuses, and this is not strange, because our bodies are around 300 Kelvin, where so the frequency the peak frequency is is in the infrared range. So we are powerful infrared emitters, specifically infrared. Of course, at all frequencies, but specifically infrared. So that's why this just measured intensities, just like that. Measured intensities, and if you understood the details of black body radiation, you see that from intensity, assuming that it is a black body, you can measure, from a measured intensity, you can measure temperature. That's exactly what this, so it's useful also. It is very apt to this, to these very times that we are living through. So just, you have a couple of days, just carry this out, and we will see next time also the previous exercise that I already assigned you. I give for granted that I assume that at any time, if you have questions, you are always free to interrupt me. So in this very last minutes that I'm left with, I would like to go back to the scattering impact of the radiative transfer equation. If you remember, I briefly commented that including scattering, well, it makes the problem much more difficult from a mathematical point of view, because the equation becomes an integral differential equation and stuff like that. So I said at the time, okay, let's ignore for the time being the effect of scatterings. Let's just consider that the way matter can affect radiation is just both absorption and emission. Now it's the time has come that we must consider somehow the effect of scattering. Let's do it in a simple way. Let's consider a special case, which is enough to appreciate a lot of things, which is the so-called coherent isotropic case. So let's assume now, let's neglect the effect of absorption, the effect of emission. Let's just consider scattering. So photons are just undergoing scattering. Okay. In particular, it's always important to understand the meaning of words. Here we have two adjectives. One is coherent and the other is isotropic. Coherent in this case means that if you compare the frequency of the photon before scattering and then the same photon after scattering, the frequency hasn't changed. So the frequency remains the same. So the frequency, same frequency, it coherent in that sense. So there's no change. So the photon does not undergo any frequency change. So the energy of the photon remains the same. That's here in this context what coherent means. It's a simplified case, yes, of course. The second word is isotropic. Well, you already know that. It means that the effect of scattering is the same for all directions. So when we think of a photon which is going to be scattered by a given atom, we assume that the probability of being scattered is the same for any direction. Okay, that means isotropic. That's the meaning of isotropic in this case. So having declared so clearly the two assumptions that we make, we can also think of the average intensity. So if you have a field, radiation field with a given brightness I, well, if you work out the average, well, average is over the entire solid angle, and you divide by total solid angle 4 pi, I call this average intensity J nu. So J nu is nothing but the average of the intensity, average in the sense of solid angle. Well, the emission coefficient. Well, here emission is in the sense of scattering. So what I gain thanks to scattering. Why gain? Because thanks to scattering, I'm interested in studying intensity along a given direction, okay? I can gain photons just because the photons before scattering were just traveling along a different direction. Then scattering, thanks to scattering, they are scattered along my own direction. So that's why it works as a source of photons, because scattering can help increase intensity, because it takes from other direction and scatters along my own direction. This is clearly proportional to the average intensity because of the assumption of isotropic scattering. So the larger the number of photons that are traveling from all directions, the correspondingly larger is the probability that these photons will be scattered. The more photons I have coming from all the possible directions, and the proportionally more photons I will have scattered into my own direction. Of course, this proportionality is ruled by a coefficient, which in this case is denoted with sigma nu. Here I keep saying that I'm using standard notation. In particular, the textbook that I'm adopting very closely is the Rybicki-Leitman, is the first one of the list of textbooks that you find in the end. So this notation is not just due to myself. The standard notation. So here, as I wrote here explicitly, this has nothing to do with the cross section we met a few classes ago. I know that's the very same notation, but practically you always understand from the context what is the mean. Okay, so I know that it might look a little bit confusing, but as a matter of fact, it's not. So the notation is the same, but this sigma nu has nothing to do with the cross section. Is not a cross section. It's an absorption coefficient, much in the same way as alpha nu. Very same from a dimensional point of view. So it's proportional. It's proportional to the average field. Yes, the more photons are traveling from all other directions, and the correspondingly more photons will be scattered along my own direction. That's why J nu J nu scaled as capital J nu. Well, the corresponding source function is just the emission due to scattering, so what I call J nu over sigma nu. Well, sigma nu works as an absorption coefficient. Why? Well, the very same process which is responsible for scattering photons which are coming from other direction to my own directions is the very same process also which scatters photons which were originally traveling along my direction, and then they are lost from my point of view because they are scattered towards other direction. And the process is the very same. So the ability to scatter other photons along my direction is the same, which then I have to pay photons which I already have traveling along my direction, then are scattered away. So that's why sigma nu works also as an absorption coefficient. It works both ways. I gain photons from other direction, I lose photons to other direction because of scattering. The process works both ways. You gain and you lose because of the same process. And so, of course, just the source function is the capital J itself. So let's work out the resulting radiative transfer equation by neglecting, as I said, absorption and emission in the traditional sense. Let's just consider pure scattering. Of course, as we saw, pure scattering means that you gain and you lose. You have a source of gain and a source of lose. In particular, here I use two different colors. Minus sigma nu, the red one, minus sigma nu I nu is what you lose. Why? Well, first of all, note that is proportional to I, exactly much in the same way as absorption that we already studied works. You've got something that you already have and you lose. So it's something that is proportional to what you already have, which is I nu. And what you lose is described by the corresponding absorption coefficient. Given that here, the kind of absorption that we have in mind is just the only one due to pure scattering, the corresponding absorption coefficient is just sigma nu. So all this loss, this is a loss, you see, di over ds. So how much do I gain? Well, the red one is what you lose. Photons that are before scattering are traveling in your direction. After scattering, you lost them because they're being scattered away. Okay, and how many of them? Well, proportionally to I. And sigma nu it works as an absorption coefficient. The larger sigma nu, the more photon you will lose because of scattering. But at the same time, scattering helps you because it helps gaining photons that are initially traveling from along other direction, and then they are scattered along your own direction. So this is just J, what we call before J nu. But J nu is sigma nu capital J nu. So this term is just, if you think of the original, this is very, very similar to the original radiative transfer when we neglected scattering, when we just considered absorption and emission. You see, this is the term which works like the emission, the absorption one, and this is just J nu, but J nu in this case is sigma nu capital J nu. The scattering here works both ways. It allows you to gain and to lose. The source of gain is, of course, capital J nu, is the field, the average intensity. So what I have from all the other directions is the source of what I gain. The source of loss, you can lose what you already have. You cannot lose what you don't have, even if in finance in this crazy world. Okay, so you can lose also only what you really have. What you really have is I. So that's why sigma I. So putting together, now putting really everything together, so the true absorption minus alpha I. Emission is J, or here I'm focusing on the case of a thermal emitter, okay? So thermal, matter in thermal equilibrium means that the source function is a Planck function, okay? Remember that this is not the radiative transfer di over ds, so not di over d tau. So this guy here should be J nu, but J nu, if you want, Kirchhoff's law is alpha nu. This is minus alpha nu times minus b is just plus alpha nu b. Alpha nu b is J nu, my original emission coefficient. And now these two extra terms that I've just had. So the scattering adds these two contributions, one which is positive, as I said, one from one side you gain because of scattering, on the other side you lose because of scattering. You can rearrange terms and put this way, provided that you give a new definition of the source function. If you define the source function this way, it's easy, it's straightforward to check, you see. It's very easy. Well, the first term, I plus sigma nu times I nu is this guy plus this guy. The second term, S nu times this guy is just the denominator. So you are just left with minus alpha nu beta nu minus sigma nu beta nu. And you have the extra, the extra two terms. So this is a generalization. Defining the source function when in the presence of both emission scattering, of both emission absorption and scattering, I'm generalizing. It's a generalization process, okay? The source function, so, is the result of both the emission absorption properties of matter as well as the scattering properties of the same matter. In particular, the sum of the two absorption coefficients, so the real true absorption coefficient alpha nu and the scattering absorption coefficient sigma nu, is called extinction coefficient. As I wrote here, absorption, extinction, they should be synonymous, but as a matter of fact, they are used in a different way just to distinguish them. So it's just, one should remember that extinction coefficient is nothing but the absorption coefficient plus the scattering coefficient, just like that. And of course, having said that, having generalized the definition of absorption coefficient, or better, I should say, extinction coefficient, if you take 1 over, is the corresponding mean free path. So we can redefine lambda L nu as the corresponding mean free path when you consider both effects, both absorption and scattering. It's interesting to see some special cases to see whether we recover what we already know, what we expect. In particular, let's suppose we are considering a point in space which is deep inside a medium of constant temperature. In that case, what does this mean? Well, J, so capital J, so the average intensity, average over all directions, is just B. Let's consider a black body or thermal source, optically fixed, so the intensity is just black body, isotropic case. So J, capital J is the average, that is B in all directions, so the average is just B. If J is B, look at the source function. You see? The source function itself is B. The source function, which includes now also the scattering effects. So even in the case of a hear it, isotropic scattering, thermal emitter, optically thick, the source function is still a Planck function. So all what we derived when we were neglecting scattering holds true, still holds true. The other interesting case, if you take an element of matter which is isolated in vacuum, well, if you think in that case, you cannot gain scattering from other directions because it's surrounded by nothing. So you can only lose radiation. So it means that J nu, so the average of all coming from all directions is 0. So in that case, the source function is this guy. So is the Kirchhoff's law diminished. Kirchhoff's law would be just alpha nu, beta nu, b nu, sorry. In this case, it's diminished by the effect of scattering. Okay, no, I think this is already 1 hour and 40 minutes. So next time, so we'll start with the solutions of the exercise that I'm not going to share because I don't want to tempt you to have a look beforehand. So we will see together, then I will share afterwards the solution. And then we will go through the exercise of carrying out, see the relation between the number of between the optical depth and number of scatterings, and finally, we will calculate how long does it take for a photon to come out of the sun. Do you already know that? Do you already calculate? Did you already calculate in some other courses?
25 years.
How much? How long?
25 years.
No, that's too much. Of the order of 10 to 4. We will derive a few thousands, but a more precise calculation is around 10 to 4 years. 10 to 5 years is too long. So the photons that, when you sunbathe, well, today is not the proper day, but when you sunbathe, you will see that the photons that are coming to your skin were born before the ancient Egyptians, or something like that. Anyway, we'll talk about this, and then we will start talking about Einstein coefficients, which is also useful. So let me